Nice.
Okay, so the guy that we're being asked to find the interval of convergence for, the first one anyway, is this guy here, right? So I'll call him f of x. Well, it's going to be the limit as n tends to infinity. Ratio test, pretty much guaranteed. Okay, you put an n plus 1 in here, you get that guy. And here you get that guy. And then if you switch places and turn it upside down, you get that guy. These cancel and leave an x. So I'm going to be looking at the limit as n tends to infinity of n squared, n plus 1 squared, and x. Okay, let's focus on that guy. Would you agree the limit to that is 1?
Yes.
And you can either do it by L'Hopital's rule twice. You have to do it twice, I think.
Mm-hmm.
Or you can just FOIL the whole thing out and divide top and bottom by m squared. So we'll assume that it's 1.
Yeah.
So we get that. Now, this limit has to be less than 1 if it's going to converge.
Yes.
And that generates that guy, which gives me right now an interval of convergence of -1 up to +1. So what we now need to do is check the endpoints, because maybe they will work, maybe they won't, maybe one of them will work. So I'm going to check x equals 1. So I'm going to look at this, but I'm going to imagine that x is 1. And if you plug 1 in here, you're going to get n equals 1 to infinity, 1 to the power of n over n squared. That in turn is just going to become a very simplified sequence, series I should say. It's going to be that guy. Right, does that guy converge?
Yes.
P series b equals 2, off you go and do it. So I'm going to put a square bracket around that guy.
Mm-hmm.
Okay, I'll try the other one now. If you put in a -1 for x, you get this guy. Do you recognize that alternating series?
Yep.
Could you imagine that that is going to decrease to 0 and therefore it's also going to converge?
Yes.
So our final answer is that the interval of convergence of this fella is -1 to 1. And then we have to find the interval of convergence of its derivative. Well, I'll rewrite the original. They got a 1 on this? Yeah, they've got a 1 on it, fine. I would have done as whatever, right? 1's fine. Now, if you want to find the derivative, can't you just find the derivative of the individual pieces?
Yes.
So what does that mean? That essentially that means that we have an n, an x to the n minus 1 over an n squared, and I am going to move that to a 2. Whenever you differentiate a power series, you move it up 1, and you might say, well, why do I move it up 1? Because technically you're probably going to destroy the first term. The constant term is going to become 0 and disappear, and you don't want to have that still built in, right? So it's a minor detail because it doesn't really change. The ratio test doesn't care if it starts at 2 or 22. It's still the same test. But it's a slightly different looking function, right? Oh, by the way, I just noticed something that I probably should have noticed earlier.
Yeah.
So here it goes. It's going to be the limit as n tends to infinity. If you put a +1 in here, that becomes x to the n. And you got a +1 in here, that becomes n plus 1. And then you turn it upside down and you get this looking guy. And these cancel and leave an x. So now we're going to get the limit as n tends to infinity of an n over an n plus 1 x. And now we focus on that guy. Would you agree that is 1?
Yes.
So we get exactly the same result, but for slightly different reasons, that the limit is absolute value of x. So our initial interval of convergence is going to be -1 to 1. I'm just skipping writing that down. So now we'll test the endpoints. Let's test x equals 1. Now I'm testing it with this guy, right? So what does that get me? It gets me sigma n equals 2 to infinity n. If you plug 1 in, it's 1 to the power n minus 1 over, oh yeah. Let's do the simplified version there. Wait a minute, isn't 1 to the power of n to the power of 2n to the power of anything you like still 1?
Yes.
Wait, so that guy is a p-series. It's a p-series with p equals 1. So this guy diverges. Right? Which means that this stays put. You can't use 1.
Mm-hmm.
Now, if you plug in -1, do you recognize an alternating series that decreases to 0 and therefore converges? It's an alternating harmonic series, but it's still alternating, right? And it goes to 0. So by the alternating series test, this does converge. So it means on this side, you get a square bracket, because you can be used, right? So -1 can be used, and the other side it's 1. That too quick on this one. This guy is right. This guy is alternating. Why? Because -1 to the n, -1 to the n plus 1, or any combination you can think of. That's basically going to generate the plus or minus. Do you recognize? Actually, that's one of the first alternating series that we ever do. Because for an alternating series to converge, it has to have a limit of 0. So 1 over infinity gets you 0. And it has to decrease. And we're talking about the untouched value, right? So the 1 over n bit is the bit that has to decrease. And a half, and then a third, and a quarter, you can prove that decreases. You put that package together, decreases to 0, converges. That was my logic.
Yep.
And square bracket, curve bracket is the interval of convergence of that fella. Are we good?
Yes.
Now, I'm just going to write down the first derivative now so that I can differentiate it. And the first derivative starts at 2, finishes at infinity, looks like that. If I take its derivative, up at 1, right? When you differentiate a power series, you lose the first term because a constant becomes 0, the same argument as before. Multiply by the power, reduce the power by 1. We get that guy, right? I'll do the limit as n tends to infinity. I'll do the ratio test. In this case, it's a little bit awkward, but basically, an plus 1 says use this formula, but replace all the n's with n plus 1, right? So let's see what we get. N plus 1, take away 1 gets you n. X to the power of n plus 1, take away 2, still leaves you with an n minus 1 guy. And n being replaced by n plus 1 gets you that guy. And then the reverse one is basically this guy, but turned upside down. N, where we go, n minus 1, and n minus 2. And you just have to be a little bit careful about the cancelling here, because it's easy to cancel an x to the n with an x to the n plus 1 or something like that, because it's easy to keep track. But this x to the n minus 1 will cancel this x to the n minus 2.
Mm-hmm.
And it will still leave behind an x, which kind of you expect to get, because you always kind of get an x, don't you? And these two guys give me n squared, and these two guys at the bottom Well, if I FOIL them out, because it's not hard to do, you get n squared minus 1. Would you agree that that's 1 again for the same kind of reasons that all the other ones were 1? And would you agree that we're getting deja vu here because for a different reason yet again, we still get that the answer to the limit is absolute value of x, and that will converge when it's less than 1, which means our interval of convergence is going to start life like that. And then I'm going to test these two, but with that guy, and let's see what happens. If you put x equals 1 into here, you get sigma n equals 3 to infinity, n minus 1 over n, and let's skip a line. Won't 1 to the power of anything just be 1, so that's all you're going to get left with. 1 to the power of n minus 2 is always going to be 1. Doesn't matter what value n is.
Yep.
So that means we get this guy. If you look at this guy really carefully, can you see he diverges?
Yes.
Right. By divergence test, isn't his limit 1? Now, if you put in x equals -1, you don't get much better. All you get is -1 to the n minus 2, the same two terms. And since this diverges, doesn't the whole thing diverge as well? So 2 diverges means that your interval of convergence is doesn't include the 2 endpoints. So the original function, both endpoints were in the interval of convergence. When you did the derivative, only the -1 side survived, the other one was curved. And when you go to the second derivative, they're both curved. I'm not doing it, but I could make a pretty good prediction here. Do you know if I did the third, fourth, and fifth derivatives, they would all come out like this as well?
Yeah, I'm guessing so.
But we're not doing it because who wants to? Did that help?
Yes, that does help a lot. Just like showing the different kind of tests as you know, have different x equal values.
Right.
Helps.
Yeah. From my experience, at least, the most likely situations you get when you're plugging in these numbers are alternating series, p-series, or divergence. And,
yeah.
I mean, there will be exceptions to everything. If I see a factorial floating about, then I might be a little bit concerned. But normally, this process here destroys the factorial, so we shouldn't need to worry about that. This bit here takes care of the factorials. If this had a factorial in it, you'd really have to work quite hard on it because it would converge because, factorials kill everything. I make them tiny, and tiny is good in this world because tiny means that the series will be, it will exist, right? It won't be divergent.
Yes.
But I don't think they've got factorial. Maybe they have and I missed it. Okay, where's your next question go? Oh, well, we do have other companies, so we should share out the wealth. Matthew, you got a specific question you want to go over? Or you just want to watch?
Yeah, I was having trouble on one. Let me find which one it was real quick. Okay, so it's 11.8, number 14.
Okay, let me go hunting for that one. 11.8, number 14. If it's an easy to write question, I'll just write the question down rather than zoom back and forward. The version I've got might not be quite yours, but it'll be the same genre. So I have an n. I have an x minus 2. You might have an x minus 3 or x minus 1 or something. And on the bottom, I've got an n cubed plus 1. And the limits are from 1 to infinity, which is fine. Okay, and we're being asked the classic interval of convergence and radius of convergence question. Right, so we're going to do the ratio test. Yeah, ratio test in this one. So it's going to be an plus 1 on the top, an on the bottom. Okay, You take these terms and you replace all the n's with n plus 1. So this guy becomes n plus 1, x minus 2 to the power of n plus 1, and n plus 1 cubed plus 1. So that's that bit done. Now the divide by an, the way I do that is I basically take this guy untouched and just turn him upside down. That's pretty much what happens. So I'm going to have an n cubed plus 1 on the top, and on the bottom I'm going to have an n. I'm going to have an x minus 2 to the n, and we go like that. Not that you need to know this for this particular question. Do you know that's a Taylor series centered at 2? You know, if you were trying to describe it. When it's x to the n, you can either call it a Taylor series centered at 0, or you can just say it's Maclaurin series, because if it's centered at 0, it's Maclaurin's. So let's see what we get here. There are going to be some pretty messy, well, actually, maybe not. I've changed my mind about that. I'm going to cancel this guy with that guy. If you cancel an n plus 1 power with an nth power, don't you leave one of them alive on the top?
Mm-hmm.
I'm not going to do anything really spectacular to the rest. All I'm going to do is kind of put them together. So if you take this guy and this guy, what you get is n plus 1, n cubed plus 1. And if you take this guy and this guy, what you get is n plus 1 cubed plus 1. Right. Now, this is a really horrible mess, but if you think about it, this limit will be 1. And my argument for why the limit will be 1 is that if you FOIL this whole thing out, the biggest power of n you get is n to the 4.
Yeah, it would be.
And if you spent a lot of time and effort, wouldn't the bottom be eventually n to the power of 4?
Mm-hmm.
And when you are doing polynomial divided by polynomial, isn't it only the biggest power of n that matters? And you've got a 1 n to the 4 on the top and a 1 n to the 4 on the bottom. So I'm just going to say that's 1. And that means that's kind of how I got to there without doing too much work.
Real quick question.
Yes.
So if we're doing this and we're showing our work for like our final, can we just show that the highest polynomial is n to the 4th, and then on the side do 1 over n to the 4 and then cancel things out? Or do you want us to FOIL everything out?
No, don't FOIL everything out. In fact, maybe even less than you said. See, from this line to this line, you could just put at the side, leading coefficient top and bottom is n to the 4.
Okay, yeah, so that's kind of what I've been doing. I was just making sure that that's okay.
Yeah. I mean, if you were going to, but we're not, if you're going to do it really, really formally, like if a lawyer was sitting over your shoulder, theoretically, you should have taken this and done a whole load of side work all the way to the end with foiling it out in L'Hopital, whatever way you would do it. You'd still get 1, but that would have been a much more formal proof. I think in these cases here, especially these ones, that's what you're doing. Now, rewind. If this isn't this question, but it is a question, what is the limit of that ugly bugger? Right, that's the only question, right? What's the limit of that weird polynomial? Then in those questions, that's whatever that was, 11.3 or something, right? Wherever they appear. I would expect you to do the L'Hopital, FOIL it out, all that good stuff.
Okay, that makes sense.
It depends on the context, where it is. In
Okay.
this case, that's just a sub-issue. The main context is this, right?
Okay.
Getting to here. Right, now, according to the ratio test, if this is going to converge, doesn't it need to be less than 1?
Mm-hmm.
This becomes a slightly more awkward inequality than just an absolute value less than 1. It's this guy in the middle is between 1 and -1. What you then have to do is isolate the x so that you can get the interval. And so what I'm going to do is I'm going to take this multiple inequality and I'm going to add 2 to all pieces. And it now becomes this guy. So if you add 2 to that, you add 2 at the middle, and you add 2 at the end, it now becomes that guy. That is now my interval of convergence. It's 1,3, or at least it's the beginning of it. We still have some checking to do. How about R? the radius of convergence is just 1. Is that right? Yes. Can you imagine where the middle of this interval would be? Wouldn't it be at 2? And you'd go 1 either side? That's another way of looking at it. Very often, if this has just got an x in it, whatever this number here is probably going to be our radius convergence. In a lot of cases, it's 1 because the circumstances. But I can imagine some situations where you had to divide both sides by 2 and get a quarter or a half or something. But there we go. Now, we're not finished. But we have to test the endpoints. So I'm going to test x equals 1, which means you go back to the original, which is this guy here, and you make x equals 1, and let's see what you get. You get an n. 1 take away 2 is -1, so I guess you get -1 to the n. And on the bottom, you get n cubed plus 1. So all I've done is take this fella and replace the x with 1, and I now have that. I'm not going to write it, but to me, I think that belongs first and the n belongs second, but that's just cosmetic. Do you recognize is an alternating series here?
Mm-hmm.
Would you agree that this alternating series is decreasing and its limit is 0?
Yeah, I think so, because that's a cubed on the bottom, so it just
And it's going to be at the top, right? So it's its limit equals 0 and it's decreasing. You put that package together, then doesn't that mean this converges?
Okay, yeah, it does.
So that means that we can now go to here and say, you can use -1. So that means that's a square bracket now. Now I'm going to choose the second filler. The second filler was 3, right? And it now becomes n equals 1 to infinity. 3 take away 2 is 1, right? 3 take away 2 is 1. 1 to the power of anything is still 1. So basically, you just have this fella. Okay, is that going to converge?
Oh shoot, that's a P series. I always get them
It
mixed
is.
up, but
It is a P
it's
series.
P equals 2, so
Right.
I don't remember what that is. It might be
P equals 2's converge.
okay. Oh,
Right.
because it goes to 0, right?
Well, they all go to 0. The P equals 2 is that anything bigger than 1 converges, anything less than or equal to 1 diverges. And it's actually a comparison to it, but that's nitpicky comparison. And it's a comparison to P equals 2, right? So it converges. Which means then that both of these endpoints are usable. And the question is finished.
Okay. Yeah, that makes sense. I think my biggest trouble was the really weird like end part with the into the force that you just canceled out, because I didn't quite know what to do with all that. But yeah.
This stuff over here?
Yeah,
Yeah.
That makes sense now, though.
Right.
So, thank you.
And yeah, whenever you're doing one of these power series, forget about this guy, but see if everything that's left is just powers, like n squareds and n cubes and stuff that look like that. You will get 1 out of it, essentially. And the reason that you'll get 1 is that if you have an n cubed and the other guy's an n plus 1 cubed, when you stick them together, isn't the limit always going to be 1? And you can make it as ugly as you like on the top and as ugly as you like in the bottom. You just end up getting 2 guys that are almost identical. The only difference is one of them is plus 1 more than the other would have been. And that's not going to do much when you go infinite on people. It's still going to level off at 1. So polynomials are pretty easy to predict what you're going to get. I can look at that question and pretty much guarantee that's going to be the answer at the end, which it is, remember? If there's factorials involved, 2 to the n's involved, anything like that, all bets are off. You could get all sorts of answers out of those situations, right? So you really do have to be careful where you're cancelling and keep on top of it. But normally a factorial in the bottom will get you a limit of 0. which case the interval of convergence is everybody. And if you stick a factorial, like an n factorial on the top, right, if you do that, an n factorial on the top, you'll probably find the limit is infinite. And when the limit is infinite, it means it diverges all the time, except when x is whatever the center is, 0 in this case 2. So those two extremes are actually less work, because you don't need to test endpoints because there won't be any. So in a perverted kind of way, you want that to happen because it makes your life a lot easier.
Mhm.
Okay, what's our next guy? Aviel, you got a question?
Sure, Professor. I just have like some general questions.
Sure.
So when we're doing a comparison test and we want to show that A sub n is smaller than B sub n, how far would you like us to prove it? Because like most of the time I just say like the denominator is bigger, so it will be smaller, or such that. Like, do we need to actually show
I'm just making one off the top of my head. Suppose you had n cubed plus 1 and you had an n to the 4 plus n, right? Right, and that's your en guy, right? And
Yeah.
you want to prove that this is bigger than what would probably be the, well, let's jump backwards a bit. Wouldn't that guy behave like a 1 over n?
Yeah.
And so you know it's going to diverge then. So you want this to be bigger than 1 over n. So your question is, how do I prove that? All you need to do is show me that you're going to take this guy and you're going to essentially convert it. So how do I make this guy smaller? Right. Well, there are two ways to make this guy smaller. Can I make the top smaller?
Yeah, you can subtract the 1.
And subtract the 1. And can I make the bottom bigger? Now, the best way to make the bottom bigger is to do that.
Right.
And this guy now becomes that fella, and then off you go. The half doesn't matter, right? It's the 1 over n that matters. So that would be all I would be expecting here. I would expect you to show me what the top and the bottom transitions are. Let me take that same question and just alter it enough to make a difference. Almost the same guy. I just made this guy 5 now, right? Now, if you look at a quick comparison, can you see it's going to be a 1 over n squared?
Yeah.
Now, 1 over n squares converge, don't they?
Yeah.
So do you see my goal now is to go the other way? So if you want this to be bigger, don't you make the top bigger?
Yeah.
And you make the bottom smaller. And off you go. So not that much, really, as long as it's polynomials, which I think most of these questions are, aren't they? Polynomials, top and bottom. You only really need to show me this thing. You can make something bigger by doubling it, doubling the highest power, and you can make something smaller by halving the largest power.
Okay, cool.
And that tends to take, because some of them are like n cubed plus 4n squared plus 5n plus 7, and really you don't care about the rest. If you just double the top one, it's bigger. If you half the top one, it's smaller.
All right. Yeah, I'll keep that in mind when I take the final.
Gotcha. Any other questions? Are you good?
Yeah, just a quick another general question. When we're doing the alternating series test, do we have to prove that it's decreasing to like a big extent, or can we just like?
No, you must prove it. So that means you're going to have to go f of x equals 1 over x squared or whatever it is, differentiate it, and then you do that kind of plus minus trick that I did. Do you want to see one?
Yeah, sure. A quick one would refresh my memory. Thank you.
Okay. Right. Suppose that you were doing an alternating series like this guy. Then the real valued function is the real valued equivalent function is this fella, right? So the math says that this will behave the same way that does. So we're going to have to differentiate it. So this would be part of your working. So it would be f dash g. Take away f of g dashed over g squared. That guy gets you 1. This guy you leave alone. This guy you leave alone. This guy you differentiate and get 2x. And you get an x squared plus 1. My pens are running out here. I need to get new pens here. So tidy up the top a little bit. X squared plus 1, take away 2x squared. I believe you end up with this fella. Right, so that's the derivative. Now, typically, you have a restriction over here which says I only need to prove that the derivative is negative when x is greater than or equal to 1, right? Because the sequence typically starts at 0 or 1, right? But you're allowed to bend that a little bit. So if you want to just be safe, pick a big number like 10, right? It's allowed. Right, now, would you agree that 1 minus x squared is going to be negative when x is 10 or bigger?
Yeah, it's gonna
Yeah.
be negative.
So I'll just stick a negative there to represent that. Would you agree that x squared plus 1 all squared is positive no matter what you do?
Mhm.
And isn't a negative thing on the top with a positive thing on the bottom going to give me a negative answer?
Yep.
And isn't a negative derivative mean it's decreasing?
Okay.
So that's how you prove decreasing. You prove the derivative is negative, and at the end you're probably going to have this little plus minus trick here, where you just take the bits that it's made from and state, if it's true at least, whether they'd be positive or negative under the condition that x is greater than or equal to some number. It's nice if it's 1, and that's great, but if you need to do 2, 3, or 43, it's still okay.
Okay.
Because it's not uncommon for an alternating series test to go up a couple of times before it starts heading south and decreasing.
And just a quick thing on that. When we're doing a power series, and we have to check the endpoints, and we have to use an alternating series test.
Yeah.
Can we just assume that it's decreasing, or should we also prove that?
You just missed the exact same question.
Right.
Kevin, do you want to tell them in your words what's the rule for that?
That we still have to go through the steps to
Okay.
make sure it's decreasing.
Okay.
Sure. Thank you.
Okay. So, Travis, looks like your turn if you have a question, or you're just listening in and whatever.
Yeah, I'm just listening in, thanks.
Okay, I think we'll go back. I'm doing it in Kevin, Matthew, Aviel, Travis. So, Kevin, it's back to you again. What you got?
Awesome. Let's take a look at 11.10 number 3.
Okay, 11.10, number 3. Let's see. Okay, what's my version of 11.10? Whoa, okay. Use the definition of Taylor's series to find the first 4 non-zero terms of the function f of x centered at the given value of a, and express your answer as a common separated list. Okay, so they don't want you to stick pluses or minuses between them. They just want you to write them down with commas. Do you know they should have just got you to write the whole thing down with pluses and minuses, but we can't do much about it. Now, the function that we're going to do that, at least the one I've been given, is 3x e to the x. So I suppose you may get 5e to the x or something, but it'll be in that family.
Yep.
So it's centered at 0, which technically means it's also Maclaurin series if you're centered at 0. That's probably the easiest one to get derivatives values is when x is 0. So I guess I should do the derivatives. Okay, if you do this fella, this is going to be a product rule. So it's going to be f dash g plus f of g dashed, which means it's going to be 3e to the x plus 3x e to the x, which I'm going to combine by taking out a common factor of e to the x. Now, if I do the second derivative to this guy, I'm going to get f dashed, which is 3 e to the x, plus 3 plus 3x e to the x, which gives me 6 plus 3x e to the x. And then I'm going to use patterns. First derivative, second derivative. If you don't feel comfortable about patterns, then just differentiate it in the usual way. Now, I'm only going to be asked to find, I believe, the first 4 non-zero terms. So let's see what we get here. If you plug in 0 here, isn't f of 0, 0? So that doesn't count. If you find f dashed of 0, you plug in 0 here, you get nothing, but 3 here, and e to the nothing, you get 3. If you plug in 0 here, in the second derivative, you'll get 6. If you do it to the third derivative at 0, you're going to get 9. And since I need 4 non-zero terms, I think I need one more derivative because of that. Anybody want to take a guess at what goes in the brackets just by using patterns?
Yeah, 12 plus 3x.
You know, if you see some, you know, makes your life easy, go for it. Right, now, these guys get plugged in to a fella that looks like this. That's Maclaurin series. If you write Maclaurin series out in full, it looks like this. And in a lot of ways, I think it's easier to see it when it's written this way. Technically speaking, this series goes on forever. That guy is 0. This guy is 3. 3x over 1 factorial gets you 3x. This guy here is 6. 6 divided by 2 factorial is also 3. Oops. This guy is 9. 9 over 3 factorial. 9 over 6. 9 over 6, 3 over 2. This guy is 12. 12 over 4 factorial. 12 over 4 factorial. 12 over 24. You get a half. What I've just done here is I have basically written down the first 4 non-zero terms of the Maclaurin's expansion of this guy. What the book does is that they want you to just go 3x, 3x squared, 3 upon 2 cubed, and 1/2 x to the 4, and you're done.
Okay.
I think that would have been a better version of the answer, but I have no power over the thinking book.
Yeah, I guess the wording was just kind of confusing. I didn't know that that's what they were asking for. That makes a lot more sense now.
Good?
Yeah, that one's good.
Okay. You got another one?
Yeah, from the same section. I would just like to take a look at one of the Maclaurin series.
Okay, which one?
Let's do 6.
Okay. So find the Maclaurin series for f of x. In my version, it's going to be the natural log of 1 plus 4x. Now, to get Maclaurin's, you basically, all you need is to find out who that guy is, because these two are going to be what they are, right? These aren't going to change. So I'm going to take this guy and I'm going to find this first, second, I don't know, as many derivatives as I need evaluated at 0 until I think I know what the nth derivative at 0 would be. And once I'm pretty sure I have a formula for the nth derivative at 0, I'll plug it in here and we're finished. So f of 0 is the log of 1, which is nothing. That's not much use to me. If you differentiate this guy, don't you get 1 over 1 plus 4x? Do you get anything else?
Yeah, times 4.
Now, if you plug in 0, that guy gets you 4, right? Now, I'm rewriting f dashed of x, and I'm rewriting it in this format just to make differentiation easier. If I leave it in this format, do you know I'm probably going to do the quotient rule, and the quotient rule is a lot messier and longer. So if I leave it in this form, can't I just do chain rule after chain rule? So let's see what we get. Now we can move on to a second derivative. Multiply by the power, reduce the power by 1, and then times by 4. And I'm not going to call that guy 16. I know there's a big temptation. I'm just going to call him negative 4 squared. So when I evaluate the second derivative 0, basically that just gets you 1. I now have negative 4 squared. Now I'm going to skip some work here. F of 0 is 0. F dashed of 0 is 4. The second derivative at 0 is negative 4 squared. And I know that might be a big jump, but maybe it's not. Well, maybe it is. I'll take that back. It probably is. Let me do the third derivative, and then we'll look for patterns. Maybe I should do one more. Now, if you want to find this guy's derivative, won't it be negative 4 squared times negative 2 times 1 plus 4x to the negative 3? And if I tidy that up, I wish I gave myself more room. If I tidied this thing up, what I get is positive again. Oh, times 4. Don't I get positive 4 cubed? Times 2 times 1 plus, well, that's it. That's what you get. This is the fourth derivative. Negative 4 to the 4. 1 times 2 times 3. This is the fifth derivative at 0. Positive 4 to the 5 times 1 times 2 times 3 times 4. Never multiply anything together. Try and leave it as the calculation that you would need to get that answer. Right, so don't call it 16, call it 4 squared. Don't call it 6, call it 1 times 2 times 3. Now, if you look at this pattern, maybe we could come up with a pattern for the nth derivative. Right, take one at random. Would you agree that the answer alternates between pluses and minuses?
Yes.
So I want an answer that has, when you plug in n equals, I'm going to actually probably start at 1. So you might say, why am I not going to start at 0? If you start at 0, you'll get that term, and that kind of spoils the pattern, right? So I'm pretending that's gone. So that's just a little tweak. Right, I want a positive when you plug in 1. I want a negative when you make n 2. I want a positive when you make it 3, and I want a negative when you make n equals 4. So all I need to do is figure out whether I use that guy or whether I use that guy, right? Which one of them gives you a positive value when you plug in 1?
N plus 1.
Okay, so that means I got that bit sorted out. Moving on. If the second derivative gives you 4 squared, and the fourth derivative gives you 4, 4, and the fifth derivative gives you 4, 5, would you agree that the nth derivative will give you 4 to the n? Can't really see it in the first couple, but by the time you get to the third and fourth, you begin to see it. And this guy here is basically 1 times 2. So the third derivative gives you 1 times 2. The fourth derivative gives you 1 times 2 times 3. The fifth derivative gives you 1 times 2 times 3 times 4. Do you recognize a thing that looks like 1 times 2 times 3 times 4?
Yep.
It's called 4 factorial, right?
Yep.
But the fifth derivative gives you 4 factorial, right? So it's not a perfect match. So what will the nth derivative give me?
N minus 1 factorial.
And now you've got the guy that goes here. So our fella is n equals 1 to infinity, the nth derivative at 0, x to the n, all divided by n factorial, right? Because it's part of the formula. And not uncommon for this to happen. Is there some cancelling I could do here? Some simplification? Can n minus 1 factorial cancel with n factorial? How about that?
Yes.
Yes. Now it's a little bit messy, but something's going to get left behind. And won't it be in the bottom?
Yes.
And won't it be just one term n? Can you see that?
Yep.
Right.
Yep.
So if you can't see it, 1 times 2 times 3 all the way to n minus 1, that's n minus 1 factorial. And then 1 times 2 times 3 all the way to n minus 1 and one more, death, 1 over n, right? That's the argument. So what we now have is this fella, over n, x to the n. You've now created from scratch the Maclaurin series for that function centered at 0.
And then it asks for the R of that. Would the R just be
Just do the, it might be, I don't know yet. You'd have to do the ratio test, you know, the limit n plus 1 over an thing.
Mhm.
It's probably 4 or a quarter, or I wouldn't want to argue, I don't know. I'd have to try it.
Yep.
But it'll be one of those two. It'll either be 4 to negative 4, right, that one, or it'll be a quarter to negative a quarter, because of that guy.
That makes a lot more sense. I just had a hard time figuring out how to find what to plug in.
There is so much in this that is kind of one-offish. Trying to discover a pattern is not a fixed process, because patterns could be anything, right? In this particular case, the pattern was pluses and minuses. I got that pretty early. And then there were powers of 4. That didn't take too long. I think what took the longest is to realize that there was a third pattern going on, like a 1 times 2 times 3, and then the next time it was 1 times 2 times 3 times 4. And so don't shortchange yourself and just do the first and second derivative and think you've got the pattern. Because if you did that in this question, wouldn't you probably not notice the factorials?
Yep.
And this is just this one. God. Because patterns are kind of unique, I don't know what the next pattern is going to be. Maybe the next pattern is just 1 over n squared. You know?
Yep.
Maybe.
That makes a whole lot more sense. I got lost in the factorial part of this question, and breaking it down like this was helpful.
Right. If you ever do a factorial top, factorial bottom, they will cancel. But if you have problems of figuring out what's left over, maybe, just write the general.
Just gotta write it out.
Just write it out, and there's going to be carnage. You know, when factorials fight with each other, most things are dead, right? One guy will live, right? One guy will survive. At least one guy will survive. And if the bigger of the two is on the top, then whatever is left is going to be in the top, right? And if the bigger factorial is on the bottom, so n plus 1 will be an n, you know, an n minus 2 and an n minus 1 factorial. The n minus 1 is going to win. And what's left over depends on what you get when you cancel everything else out.
Yep.
Okay, Matthew, you got a question now?
Yeah, mine's the same section, but number 5. I cannot figure out the pattern. I wrote out like the derivatives and then what they equaled, but yeah, just.
Okay, so we have a 9. Call that 1. I got kind of bent. That fella, right? And we are evaluating this. Oh, since it's Maclaurin, we know we're going to evaluate it at 0. That's fine. Okay. So don't multiply anything. So leave everything as a calculation. So if you do the first derivative, you'll multiply it by -2, right? Reduce the power by 1, and then won't you multiply by -1?
Yeah.
General. And the two negatives cancel out. So what you're going to get is 2 times 9 times 1 minus x to negative 3. And that's the first derivative. Now, if you evaluate this first derivative at 0, you will get 2 times 9, because that ends up being 1. Right, we'll move on to the second derivative. Multiply by the power, reduce the power by 1, and then multiply by negative 1. And what that gets me is 2 times 3 times 9, 1 minus x to negative 4. And if I evaluate that guy at 0, I'm going to get, I'm going to put in a 1. 1 times 2 times 3 times 9. If I do the third derivative, I will get eventually 1 times 2 times 3 times 4 times 9 times 1 minus x to the power of negative 5, and that derivative at 0 is 1 times 2 times 3 times 4 times 9. I think I see a pattern. So here goes. Have you noticed that this 9 is 9 and never really is anything else? So that's just going to be 9. Do you recognize 1 times 2 times 3 times 4?
Yeah, that'd be a factorial of some sort.
Right, and what factorial is 1 times 2 times 3 times 4? What number factorial is it?
4 factorial.
Now, isn't this guy, if you stick a 1 at the front, 3 factorial, right? If you stick a 1 at the front, isn't this guy 2 factorial? So what does that tell me? That the third derivative gets me 4 factorial, right? The second derivative gets me 3 factorial. So I should be able to figure out what the nth derivative gets me.
So it's the n plus 1 factorial?
Yes.
Okay.
And I would probably stick the 9 at the front because it just looks nicer, right? Now, Maclaurin series has the nth derivative at 0, x to the n, all over n factorial. We now have a formula for what that is equal to, and so I'm going to plug it in. It's going to be 9 plus 1 factorial over that guy. And just like we did in the last question, can't we cancel these down and simplify them? So an n plus 1 factorial on the top is going to cancel an n factorial on the bottom. And can you imagine what would be left over after that cancelling is finished?
Not sure, actually.
Okay, here goes. N plus 1 factorial would mean 1 times 2 times 3. You get to n, and then you'd finish with n plus 1. N factorial is 1 times 2 times 3, but you'd finish at n. Death. Only one guy lives. And there isn't even a fraction there. That's your answer.
Okay. So my problem was I was multiplying like the 2 times 9 out, so I just had numbers and there's no pattern that I could see, and I was really confused.
Yeah, I think the key trick, if there's one thing you got to get from the last two questions, is don't calculate things. Only write down what the calculations are. And by that I mean, don't call it 16, call it 4 squared. And don't call it 6, call it 1 times 2 times 3, because in that format you will see a pattern. If you multiply them all together, then the digits just look like it's big, but there's no discernible pattern.
Yeah, thank you. That helped a lot.
Okay. Avio, you got a question now?
I just have another quick question.
Sure.
In previous lectures, you showed us some like magical like tricks on simplification. Could you just like remind me again if you know some of them?
It's too vague because I don't know what
Yeah.
magical tricks you're talking about.
I can
If you
do
could
the
give me an
example.
example, I
Yeah.
could do it from that.
One sec, let me
Right.
see if I can pull it up. Okay, so the limit of n goes to infinity of 1 plus 1 over n to the nth
Right.
power is e?
Yeah.
Okay.
Okay. This is a generalized version of what you just said.
Okay.
The limit as n tends to infinity of 1 plus a over n, all raised to the power of bn, is e to the a b. Right?
Okay.
That's just what it is. Okay.
Right.
And the other magic one, which I don't think really gets used anywhere much, is that one.
Okay.
Right.
I was doing the homework, and one of them that came up, I think it was 11.7, I think.
Mm-hmm.
Give me 1 second. There's
Yeah,
like
this
another one.
this does pop up from time to time.
This one?
the top one.
No, the top one, yeah. The top one, I wouldn't be surprised if you see that now again. You might see that one in an nth root test occasionally. Actually, you might see that in an nth root test as well. But my gut feeling is that if it did appear, would probably appear in some 3 to the n over n kind of story, you know? Because if you did the nth root test and that, wouldn't you just get 3 over n to the 1 over n, and that would get you 3, right? That's just off the top of my head, imagining a situation where that might be important. Right.
So there's one that's like n plus 1 to the 1 over n. I think that just goes to 1 all the time, right?
Right, n plus 1 to the power of
The whole thing to the power 1 over n.
that guy? Yeah, that does go to 1.
Okay.
Um,
I think that's it for me. Thank you.
I think if you think about it,
Mm-hmm.
if we're talking about the limit as n tends to infinity, do you think infinity and infinity plus 1 are going to differ very much?
No, you're right.
So yeah, that wouldn't bother me. It might bother me if you stuck a 2 in front of that, because then I think you'd have to be a little bit more careful, but that would
Yeah.
be a different story.
I think on 11.8, number 11, they had 7 n plus 1 to the 1 over n, and I just used the rule.
Right, and how came out okay?
Oh, what's that?
Did your answer come out okay because you
Yeah,
used
it
the rule?
did. Yeah, it just converged to 1.
So if you're in the final or anything and you use them, they're just accepted as you don't need to prove them.
Okay.
If
Cool.
you were
Okay.
interested in how to prove that, or even how to prove that, you could I could show you, but it's up to you if you want to know or not.
Yeah, I
Sometimes,
actually looked up the second one, and you had to take the natural log of.
yeah, that's
Yeah.
it. Basically, you take the natural log of the top one as well, then you get the
Okay.
answer, and it ends up being AB.
Cool.
And then you say the log of the answer is AB, but the original answer is e to the power of AB. So that's kind of how it works.
That makes sense. Thank you.
Okay. Where are we on to? Travis, you got any questions yet? Are you happy?
Yeah, I think so. Thanks.
Okay. Aaron, what about you?
I had a question about the final.
Okay.
I was just wondering if you're going to like split it up evenly throughout the chapters, or are you going to make
No.
it heavily on like limits?
I'm going to make it heavily on the last 3 weeks.
Oh, okay.
So think 60-40.
Okay.
So 60% of the questions are going to be from what you did after the midterm was finished, and the other 40% roughly. I mean, don't quote me, it could be 5% out or whatever, but that's roughly what it's going to be.
Okay.
It'll still be chronological. So the first questions will be from week 1, and the last questions you'll see are the stuff here, the Lawrence and Taylor series and so forth.
Okay, that'll help out then. So it won't be like all scattered.
No, it won't be all scattered.
Okay. Thank you.
You're welcome. Okay, back to Kevin again. You got another question, Kevin?
Yeah, I think this is my last one. We were just actually talking about this question. 11-7, number 11. It was. I think I just got lost in the sauce.
The weeds.
Yeah.
Yeah. I have done that too, so you're in good company. Oh, this is strategies for testing. Is that the one? 11.7?
Yeah.
Question 11? Okay, let me see what that one looks like. Hopefully it's some I don't need to write much, in which case I don't need to jump back and forward. Whoa, that's a good one.
Yeah.
I know what, thankfully, my brain has told me what test to use. The proof of it is not as bad as it looks. For something that's got a factorial, it's 99% ratio test. Agreed? Things with weird powers to n are 99% of the time going to be nth root tests. But here we have a monster that could be one and it could be the other, but it's going to be an nth root test.
Okay.
So I'm going to do the limit as n tends to infinity of the nth root of n factorial to the n over n to the 3n, right? It's that guy. Now, why I chose that one rather than the ratio test? Well, practical purposes, can you imagine how ugly that would be if you had to do an an plus 1 over an thing? I mean, it would just be horrendously ugly.
That's what I did.
Oh, well, the nth root of n factorial raised to the power of n is just n factorial, so that came out well. What would n to the power of 3n be if you took an nth root out of it? Right. Now,
Okay.
this one is infinite. And we're basically not doing any clever math except brute force. And infinity factorials will kill any power of n in the universe. That n factorial will zoom off to, you know, space, and it'll be infinite. And since it is infinite, oops, I said the wrong word there. It diverges.
Could we just, when proving this, do we just say n factorial is larger than 3, n to the 3, or?
Yeah, that would be enough.
Okay.
If you ever see an n factorial, just tell me if it is this top or if it's on the bottom, because
Okay.
basically that'll make it infinite or zero. The only guy that beats n factorial is if there's an n to the n left over. One n to the n murdered that guy.
Yep.
But that does mean, however, if you ever get a question that looks like this, can't you just say that the answer is infinite? N to the n is another special case where we can just simply say that we realize that is really horrendously big and it's going to win the battle of size.
Yes.
Okay. Well, whenever you are good, if you want to, you can hang around. If you think I've got what I need to do, then you can do that as well. I'm going to hang about for whatever other questions we have. I think it's Matthew. Who said Professor?
Aaron.
Yeah, Aaron. What you got to say?
In this case, if n cubed was on top and n factorial was on the bottom, it would go to 0.
You are bang on correct. Yes.
Okay.
In which case it would converge.
Okay. All right. Sounds good. Yeah.
Well,
Okay, that makes sense.
what would this guy do?
He would equal. Would it equal 1?
No.
Oh, would it infinite?
Oh,
No.
Oh shoot.
Come on.
1 over
Don't-
n.
Yeah. Simplify it first before you make up your mind, right? If there's factorials in the top and factorials in the bottom, simplify before you commit yourself, because basically you're saying infinity over some other infinity, and that's kind of hard to judge, right? But if you cancel them, then you can do it.
Yeah, it makes more sense because when you do the ratio test, they like cancel out on each side if they're like on like if one's on the denominator and one's on the numerator.
Yeah, they do. You're right.
Yeah, I didn't really see it in that way. So
Okay, so if there's only one place with n factorial, isn't that going to be the decider to converge or diverge, right? If it's in the
Yeah.
top or the bottom, you pretty much know which direction you're going. Same thing's true for n to the n, right? If it's in the top, if there's only one place where it lives, top or bottom, you can kind of, basically, you can just go straight to the answer, and it's pretty obvious what it would be. Do we have, maybe I should just throw home to general stuff now. Have we got any more questions? That's maybe an easier way to then go through them one at a time.
Actually,
Real quick,
factorial.
I'm sorry. You had some general advice a couple of lectures ago about choosing either nth root or
A ratio.
ratio test. What was that
Yes.
general advice again?
If you see a factorial, do the ratio test.
Yeah.
And if you see something to the power of n, like n to the n, n to the 3, n, weird powers of n, do the nth root test.
Yeah. Okay. That's what
But
I
if you
thought.
see both, you may have to decide which one looks like it's going to come out with the least amount of work. We always want to do the least amount of work in math, right?
Okay.
But in general, 99% of the time, if I see a factorial, it's a ratio test. And if I see a n to the n or 3 to the power of n squared, you know, really quite messy things, then I'm pretty sure it's going to go as an nth root test. I still refuse to call it the root test. I've just been brought up calling it the nth root test. And I like the nth root test because it tells me what the heck I'm doing. I'm taking the nth root of something, right? When it's a root test, it sounds like you're taking the square root, doesn't it? And that's not what you're doing. So if you're wondering why I continue to call it that, that's my argument for it. Any more questions?
That example that you just gave, that equals 1 over n plus 1.
Yeah.
If in the bottom on the other side it had been n plus 2 factorial.
Oh, okay. So on the top you had this, but on the bottom you might have had, say, something like this.
Precisely.
Okay. Then 1 times 2 all the way to the n. Think of n plus 2. Don't just think of the destination. Think of the road up to that. So you'll go 1 times 2. Won't you eventually get to n? And then you'll do one more. And then you'll do one more again. So that's the long version of what n plus 2 factorial looks like. Now when you do the cancelling, do you see in this case, there's 2 terms left on the bottom. Which definitely would go to 0. But let's make it weirder. Let's suppose I stuck that in that fella. If you looked at that and I said, does it converge or does it diverge? You might not know that it simplifies down to that guy. And isn't that guy a lot easier to decide if convergence or not? Isn't it a comparison test to a P series, P equals 2, and it converges? Now, I don't think I've seen a homework question like that, but there is a infinite number of things that series can look like. And so you just gotta, you know, oh, I haven't seen one like that, and figure out what you're going to do with it.
Yeah, I'm just trying to get used to the algebra of factorials too.
Yeah, there are multiplications, but in a lot of ways it looks like you're subtracting things, doesn't it?
Kind of.
Yeah, if you've got an n factorial on the top and an n plus 1 factorial on the bottom, don't you just end up with an n plus 1 at the bottom? You know, eventually. Maybe subtraction is the wrong word. You're removing things. That's certainly true. Aren't you removing things from the top and bottom by cancelling? And you're really trying to find out what's left after that process. And that's what the simplified version looks like.
Yeah, like when I look at everything on the paper, like it's not a lot of writing, but there's actually a lot of calculation to account for in that.
Mm-hmm.
Keeping track of like so much stuff.
Yeah, I mean, algebra is meant to be your friend. If you're good at algebra, algebra can get you out of a lot of holes.